Hey students, here is part 2 of today's lesson. So just as a friendly reminder, I'm in the middle of this is, what are we doing, a 5-part transformation lesson. This is part 2 of that lesson, and part 2 is reflections and the square root family, and this is part 2 of this reflections in the square root family. So this is part 2 of part 2. Kind of confusing, but let's get into some examples. So part 1 was dealing with the theoretical side of reflections, and now let's apply it. In our first example here, it says to write an equation for the given graph, and this is my given, this f of x. It's a weird looking graph, but it has 3 main points, one at 1, 0, one at negative 1, 3, and one at negative 4, 2. And we need to graph a g of x graph that is, it's same as f, but it's f of negative x plus 2. So if you recall from part 1 of this lesson, we can I showed you this transformations definition list. And in this particular equation that we're looking at, this f of negative x plus 2, on the inside I have this negative that's not hanging out with the x. So that's like this negative right here. And that negative, as we talked about before, is a y-axis reflection. So we first have a y-axis reflection. And then this plus 2 on the inside, we talked about that yesterday. That's like this x minus h. And because this says positive 2, yet this says minus h here, that means that this h value is negative 2. So it's not going right 2, it's going left 2. Okay, so back to this work right here. So I have these 3 points, and these 3 points I need to reflect over the y-axis and go left 2. And I should do that with a secondary color here. So I'm going to use red. Okay, so first I'm going to do this as if I am on team graph paper. So if I'm on team graph paper, I take my first coordinate, 1, 0. I reflect it over the y-axis, so it would bounce over to here at negative 1, 0, and then I need to travel left 2 to right here, to negative 3, 0. So once again, I reflected over the y-axis, and then I went left 2. Same thing with negative 1, 3. I reflect over the y-axis to 1, 3, and then I go left 2, which oddly enough would actually put me at this exact same negative 1, 3 point. And then this third point, negative 4, 2, I reflect it over the y-axis, so it would go out to 4, 2, and then I go left 2, and it would end up here. And then you connect the dots. And that is your g of x graph. Okay, now, before I conclude with this problem, is it okay to do the reflection and then left 2, or should we go left 2 and then do the y-axis reflection? Well, let's see. This 1, 0 point, once again, I reflected over the y-axis and I went left 2. If I went left 2 first and then reflected over the y-axis, I'd actually end up right back at 1, 0. Or let's look at negative 1, 3. If I went left 2 and then reflected over the y-axis, I'd end up way over here. So it does matter. So how do you know? Are you supposed to do reflections first or translations first? And I say, think about your order of operations. Reflections is a multiplying thing, whereas a translation is an adding or subtracting thing. We do multipliers before we do adding and subtracting, so you need to do reflections first. Reflections first, translation second, following your order of operations. Now, that's actually one reason I am on team non-graph paper, because I prefer doing these problems thinking about raw coordinates. So once again, I had this y-axis reflection, and I went left 2. If I think about what's happening with the xy coordinates, when I produce a y-axis reflection, it's going like it's flipping over a y-axis, that's changing the x value. So what it does is it creates this negative x. And then after that, it goes left 2, and if you're going to travel left, you would subtract. So negative x minus 2, comma, y. So first I applied the reflection, then I put on the translation. That's order of operations, just like I did over here with the graph paper problem. Okay, so then you take those 3 key points, 1, 0. There's a key point at negative 1, 3, and another key point at negative 4, 2. And if I apply these rules, 1 is going to become negative 1 minus 2 is negative 3. This negative 1. Negative 1 is positive 1. Minus 2 is negative 1. Negative 4 is 4. 4 minus 2 is 2. And then it says here the y coordinate's going to stay the same. So negative 3, 0. Negative 1, 3. And 2, 2. And then I would just simply graph that, thinking about where 0, 0 is. If 0, 0 is here, negative 3, 0 would be approximately here. Negative 1, 3 would be up here, and 2, 2 would be over here. Connect the dots. Label it as the graph, so this was g of x. And you have a nice non-graph paper graph. Okay, I want to do 2 of these examples. So I spent a lot of time on this one, but it's a good problem. Check out number 2, similar problem. It's going to be slightly different transformations though. But given this f of x graph, h of x equals negative f of x minus 5 plus 1. So on this one, I see that I have a negative out front in front of the function. And as we talked about in part 1, a negative in front of the function, excuse me, is that's an x-axis reflection. So I know I have an x-axis reflection, and because of this x minus 5 on the inside of the function, I know that it's traveling 5 to the right, and because of this plus 1 outside of the function, I know it's going to be going 1 up. And then, if I'm doing this on team graph paper, it's going to be a little confusing because I want to use my original F graph up here. So I'm going to start off with my negative 1, 3 up here. And like I said, do reflections first, then translation second. So if I take negative 1, 3, and I do an x-axis reflection, it would reflect down to here. And then I go 5 right, 1, 2, 3, 4, 5, and 1 up. And I do that with all 3 of these coordinates. 1, 0. I do an x-axis reflection, which actually means it would stay the same. Then 5 right, and 1 up. And then finally the negative 4, 2. Negative 4, 2. X-axis reflection, 5 to the right, and 1 up. So I have those 3 points. I connect the dots, and make sure you label it h of x. And that's how I do this problem if I was on team graph paper. If I was on team non-graph paper, well, we have this x-axis reflection, an x-axis reflection affects the y-coordinates. So, because it affects the y-coordinates, x-axis reflection, it's the y-coordinate that's being changed. So I'm going to have this negative y. There's no x-axis reflection, or excuse me, y-axis reflection, so it stays x. And then from there, you're going to go 5 to the right. And if you're going 5 to the right, you're adding 5 to the x-coordinates. And if you're going 1 up, you're then going to add 1 to the y-coordinates. So my 3 coordinates that I had, we had 1, 0, negative 1, 3, negative 4, 2. So I'm going to add 5 to the x-coordinate. So 1 plus 5 is 6, negative 1 plus 5 is 4, and negative 4 plus 5 is 1. And then I'm going to attach negative y plus 1. So negative 0 is 0, plus 1 is 1. Negative 3 plus 1 is negative 2, and negative 2 plus 1 is negative 1. And then you just quickly graph them where they would be approximately. So you have your 6, 1, your 4, negative 2, and your 1, negative 1. Connect the dots. And properly label it. This one was h of x. So check it out. Both my graph paper graph and my non-paper graph are the same, at least the graph is, but 2 different approaches to get to the same problem. Okay, I do have 1/3. What if it's a backwards problem? So, third problem looks like this. So j of x is a transformation of f of x. So I look at this original f of x, I see this transformation. Here, that's j of x, and I need to write an equation for j of x. When you get problems like this, you need to be able to kind of look at this graphically and tell, well, what's going on here? Like, what is the transformation that's going on? And one thing I'm noticing here is that this point here is my lowest point on my original f graph, yet it's my highest point here. Or my problem, or this negative 1, 3 that was on top, over here it's on bottom. And that looks to me like it got reflected over the horizontal axis, over the x-axis. So I see an x-axis reflection. Now, after this x-axis reflection, well, let's see. If I took negative 1, 3, and I reflected it over the x-axis, it would end up down here. Then, to get from here to this point, it went 3 to the right. Once again, we're following our order of operations. The reflection's the multiplier, so we apply the multiplier first. Then we think of the adding and subtracting. So it's also, after the reflection, you're going to go 3 right and 4 up to get to the equivalent point. And now we just want to put that into our j of x equation. So j of x is equal to, well, according to that guide, that an x-axis reflection is putting a positive or negative in front. For the reflection, it would need to be the negative. So it's going to be negative f of, and then if you're traveling to the right, that means that you would go with an x minus 3, just like it says here, minus h is a distance of h. So if that distance is 3, I've lost it. I've lost the visual. If we're going 3 right, according to this, it's minus h, or minus that 3. So f of x minus 3, and because of the 4 up, you'd have a +4 on the outside. Okay, so that's the backwards problem. If you're given a graph, how you'd go about writing an equation. Okay, everybody, this is really dragging on a lot longer than I thought it would. But I still have a couple more examples because now I want to apply the same thing, but apply it to the square root graphs. I have those problems written down. I just need to find them. Okay, here we go. So that was part 3. So now part 4, applying the same thing but to square root equations. So graph the function. Number 1, suppose it was y minus 2 equals negative square root x plus 3. First thing I'm noticing is that this graph is actually not in the same form that I normally present it in. So I'm actually going to do a little bit of algebra, and I'm first going to add 2 to both sides. I get negative square root x plus 3 plus 2 on the end. I like doing this little vertical thing on the end of a root to just show that the root's closed. Okay, so on this one, same thing as our previous problems, we just got to identify the transformations here. This negative out front, that affects it's outside, so it's affecting the y, so that is an x-axis reflection. Because of this x plus 3, we go opposite, so left 3, and this plus 2, we're going to go up 2. And I like showing both a graph paper and a non-graph paper approach. Here is a graph paper approach. If you think about your parent function, the parent function has these points at 0, 0, 1, 1, and 4, 2. And if I took this graph and I did an x-axis reflection, it would stay there. But then you could go left 3 and up 2, and you'll end up here. Next one, take this point, I do an x-axis reflection, left 3, up 2. Third point, x-axis reflection, left 3, up 2. And then you connect the 3 dots. Make sure you extend past the third dot to demonstrate that it is going on forever. So that is an x-axis reflection with also going left 3 and up 2. That would be a graph paper approach. I normally do, I'm on team non-graph paper. I'm not a big fan of using it. So if I'm going to do an x-axis reflection, that's going to affect the y-coordinate. So it's going to be a negative y. But then if you're going to go, so then you apply the translations, left 3, that's going to be minus 3 on the x-coordinates, up 2, that's going to be adding 2 to the y-coordinates. So my 3 key points, 0, 0, 1, 1, and 4, 2. I tend to do this one coordinate at a time. 0 minus 3 is negative 3, 1 minus 3 is negative 2, 4 minus 3 is 1. Negative 0 plus 2 is 2. Negative 1 plus 2 is 1. Negative 2 plus 2 is 0. So I have a point at 1, 0, at negative 2, 1, and negative 3, 2. And then 0, 0 is kind of your starting point, or the negative 3, 2 is your starting point. So it would start here, go like that. Oh, this is not a very good graph, my apologies. Put on the arrow, but then I need to manually write in those coordinates. 1, 0, negative 2, 1, and negative 3, 2. I normally don't even draw on the axes. I normally just draw my square root graph first the way that I know it's supposed to look because of the x-axis reflection. I know it's going to look like this. And then I manually write them in. Negative 3, 2, negative 2, 1, and 1, 0. That's usually how I go about solving these. But if you're going to do it that way, you kind of need to know what the graph's going to look like beforehand. I'd like to do one more example of this variety so I could hit up all the different types of transformations. Example 2. Let's say that it's y equals 2 plus the square root of 4 minus x. Couple things. I'm noticing that this equation does not resemble the equation that I put on this this transformation definition. This one seems to have the function first and the number second. Well, that's an easy switch. I could switch this root and this number to change it to root 4 minus x plus 2. That's not a big deal. But then also, I'm noticing that in this equation, I have this x minus h separated like that, and the negative is on the outside. So I'm also going to do that. I'm going to make that happen inside the square root by putting this 4 minus x in parentheses and then putting a negative on the outside. That essentially would make this x positive and the 4 negative. So we took this, we put like little parentheses around it, and we factored out a negative, plus 2. And once your equation looks like this and you compare it to this transformation's definitions, I have this negative on the inside. That's going to be a y-axis reflection. And then I have a minus 4, so it means it's going to be going right 4 and a plus 2, so up 2. So the inside was a y-axis reflection. Right 4 and up 2. And if you're on team graph paper, you could pull that off very easily. If I start off my first point, 0, 0, a y-axis reflection wouldn't reflect, it wouldn't do anything because it's on the axis. Then it would go right 4 and up 2. 1, 1, a y-axis reflection would put it over here, and then you go right 4, up 2. If I made them, oh, over here I want right 4, up 1. Right 4, up 2. That's the wrong dot. Sorry, start over. 1, 1, I do a y-axis reflection, then right 4, 1, 2, 3, 4, up 2. Okay, that makes sense. And then there is the point 4, 2. I would do a y-axis reflection on that, making it to negative 4, 2, then right 4, and up 2. It is confusing to me being on team graph paper, but if team graph paper works for you, you should do it. I really want to try to talk people into being team non-graph paper to look at it more mathematically. If you're doing a y-axis reflection, that's a horizontal reflection, means it's going to affect the x-coordinate. So it's going to make it negative x. But after that, you're going to travel right 4, so plus 4. Up 2 with no reflections, it's going to be the normal y-coordinate, and then you're going to add 2 to it. So those key points, 0, 0 becomes, oh actually I'm going to write them all first, 1, 1, and 4, 2. So just the x-coordinate. Negative 0 plus 4 is 4, negative 1 plus 4 is 3, and negative 4 plus 4 is 0. And then 0 plus 2 is 2, 1 plus 2 is 3, 2 plus 2 is 4. And if I'm used to a square root graph going like this, but I know that there's a y-axis reflection, that means that the graph will now look like this, and the 0, 0 point is now 4, 2. The 1, 1 point is now 3, 3. And the 4, 2 point is now 0, 4. And I don't even think this graph looks very good, but it has the 3 key points clearly labeled, and it has the right general shape, so it's acceptable in my opinion. And if we look at our graph paper graph, where the graph might look significantly different, what matters is that the 3 key points are all in the key locations. So that's another graph point. Okay, number 3. Backwards problem. So suppose you needed to write an equation for number 2. For your graph from number 2. So instead of being given the equation and being told to graph it, what if you were given this graph and you needed to write an equation for it? Okay, well, on these problems, you need to be able to look at the graph and identify what type of reflection is going on. And a typical square root graph has this look. So the fact that this graph has this look means that we reflected horizontally, in this particular case, over the y-axis. So I have a y-axis reflection. And then from there, for up, down, left, right, you could just look at the starting point. The starting point is at 4, 2, which means that this one must have traveled right 4 and up 2. And then in our guide, we've been dealing with translations in class, so I'm not concerned about that. We have a y-axis reflection, and a y-axis reflection is this negative on the inside. So I have y equals, inside the function is this negative, and then on the inside, if it's going right 4, that would be x minus 4, close and close, and that's inside the function, and this particular function is a square root. So big ol' square root around all of that, and then plus the up 2, so that's on the outside of the function, we would show this plus 2. And if we compare it to our original equation, it's the same. So that's how you could go about writing an equation if you were just given the square root graph. And that's my final example for you. Wow, students, 30 minutes for the second half of the lesson. That wasn't my intention, but I have some good news for you, is that I've covered everything I need to about transformation, or about reflections and the entire square root family. Part 1 was the theory of it. Part 2 is some focused examples. And at this point, unless you guys give me some really focused questions tomorrow to talk about, I don't have a weekend lesson. So this is the last lesson for you this week. So nothing new until Monday. So tomorrow in class, I'll actually give you everything that we need for in class on Friday and Monday. And then Friday and Monday are just going to be work days to get caught up and to understand this new complicated concept. And then on Monday night, we're going to start looking at dilations. And once we add dilations, it's going to get really confusing for a lot of people. So please make sure that you're perfect at reflections and translations before Monday evening when we're going to add dilations to the mix. So thank you very much, everybody, for staying focused for through like 45 minutes of lessons. Ouch, that hurt. But have a great night, and I'll see you tomorrow. Bye-bye.